everyone. I'm so excited to welcome you to Python Mastery. I'm your lead teacher, and together with our teaching assistant and fellow students, we're going to embark on a journey from coding basics to professional-grade architecture. What makes Python special is its Zen philosophy. It prioritizes human readability over complex syntax. In this class, we'll learn to write code that isn't just functional, but clear and elegant. Python is incredibly versatile. It's the engine behind massive web platforms, sophisticated data science models, and the latest breakthroughs in AI. By learning this language, you're gaining a tool that can take you into almost any tech field. Notice this infographic. You'll see frameworks like Django for web development and Pandas for data analysis. We'll explore how these tools form a powerful ecosystem that professionals use every day. Finally, here is our roadmap. We'll start with the fundamentals, variables, and logic, and work our way up to building a professional task manager. Before we start with the first lesson on variables, I'd love to hear your thoughts on why you chose Python. Building on our discussion about why Python is such a popular choice, let's dive into the core building blocks of the language, variables and data types. This is truly the foundation of everything we'll build together. One of the most beginner-friendly aspects of Python is dynamic typing. As you can see here, unlike some other languages where you have to explicitly state if a variable is a number or text, Python is smart enough to figure out the data type automatically based on the value you provide. Think of a variable like a labeled box. You can put an integer, a decimal point float, or even a long sentence inside. Python handles the what and how behind the scenes, so you can focus on the logic of your program. Let's look at this comparison table. We have integers for whole numbers, floats for decimals, and strings for any text wrapped in quotes. Also, notice the naming convention. We use snake underscore case, where words are separated by underscores to keep our variable names clean and readable. Does the difference between a float and an integer make sense to everyone? It's a small detail, but it's very important when we start performing calculations in our next exercise. Building on our look at the expert ecosystem and the impact of software we just covered on page 15, it's finally time to put all those pieces together. We've reached our capstone, the Professional Task Manager. This project is where your hard work across the session culminates into a functional command line application. You'll be using the OOP principles we learned on page 10 to architect the app, managing data structures from page 8, and implementing the robust error handling we mastered on page 13 to make sure it's user-proof. In this project, you'll see roles tailored to different parts of the development process, from architecting the classes to refining the user experience. Take a moment to select a role that interests you, and let's begin coding our most sophisticated tool yet. Now that we've mastered how to store data in variables, let's learn how to make our programs actually do something with that information. This is where control flow comes in, using if, else, and elif statements to guide our program's logic. The most important rule in Python control flow is that indentation matters. Unlike other languages that use brackets, Python uses spaces to define which code belongs inside a decision block. If you forget your spaces, the code won't know which instructions belong to which choice. To make those choices, we use comparison operators. These allow us to check if values are equal, not equal, or if one is larger than the other. Notice the double equals sign for comparison. That's a common spot for early mistakes. We can also combine these checks using logical operators like and, or, and not. This lets us create more sophisticated rules, like checking if a user is logged in and has administrative rights. Look at this flowchart here. It perfectly illustrates the path a program takes. It encounters a diamond, a decision point, and branches off based on whether the condition is true or false. This visual map is exactly what we are building with our code. Logic like this isn't just for computers. We use it every day. I'd like us to pause and think about how we can turn our daily routines into this kind of structure. Building on what we just covered regarding logic, we now reach one of the most powerful tools in any programmer's kit, loops. Instead of writing the same code 10 times, we let Python handle the repetition for us, making our code much cleaner and more efficient. First, let's at for loops. These are your go-to when you have a defined sequence, like a list of names or a range of numbers. You're essentially telling Python, do this for every single item in this collection. On the other hand, while loops are driven by conditions. They keep running as long as a specific condition stays true. Think of it like a sensor. While the temperature is below 20 degrees, keep the heater on. To give us even more precision, we use control keywords. Break allows us to exit a loop early if we've found what we need. Continue lets us skip the rest of the current iteration and jump straight to the next one. And pass is a handy placeholder when we want to define a loop but haven't written the logic yet. It helps to visualize how the computer actually moves through these sequences. Let's watch this short animation of a loop traversing a list. That visualization shows how the loop pointer visits each index. Before we move on to functions, I want us to think about the different scenarios we've discussed. Now that we've seen how to repeat tasks with loops, let's look at how we can package those tasks into reusable tools called functions. Think of functions as a way to avoid writing the same code over and over again. We build the tool once and use it whenever we need it. To understand how they work, imagine a kitchen blender. Every function starts with ingredients. In programming, we call these parameters or inputs. This is the raw data you give the function to work with. Inside the blender is the function logic. This is the code that performs the action, like blending the fruit. One of the best parts is that this logic is local. What happens inside the blender stays inside the blender until it's finished. Finally, you get the smoothie, the return value. This is the output that the function hands back to you. Without a return statement, the function does the work but doesn't give you the result to use elsewhere in your code. Let's look at this actual code snippet. Notice how we use def to start the definition. We have fruit as a required ingredient, but look at liquid. It has a default value of water. This means if we're feeling lazy and don't specify a liquid, Python already knows what to use. In summary, functions are your best friends for keeping code clean and organized. We define the parameters at the top, write our logic in the middle, and return our result at the end. Any questions on how the blender analogy maps to our Python code? Building on how we process data with functions, we need to talk about how we actually store and organize that information within our programs. We're now moving into Python's core data structures: lists, tuples, and dictionaries. Starting with lists, think of these as flexible, ordered bins. They are mutable, which is a fancy way of saying we can change, add, or remove items after the list is created. If you have a collection of items where the order matters and the content might change, a list is your best friend. As you can see in this illustration, each item in a list or tuple has a specific position. But remember, while lists allow you to swap items out, tuples, which we see here as well, are immutable. Once you define a tuple, it's locked in, making it perfect for data that should never change, like the coordinates of a location. Now let's look at this comparison table. Dictionaries are the third major player here. Unlike lists, they don't rely on numerical order. Instead, they use key-value pairs. It's like a real-world dictionary. You look up a specific key, the word, to instantly find its value, the definition. This makes dictionaries incredibly fast for data retrieval. Choosing between these three often comes down to a trade-off between flexibility, speed, and data safety. Understanding these nuances is what separates a beginner from a professional Python developer. Now that we've cleared the mid-course assessment, it's time to step into the expert track. Today, we're diving into object-oriented programming, or OOP. This is where we move from just writing scripts to modeling the real world. To understand OOP, look at this image of a car blueprint next to a finished car. This perfectly illustrates our first core concept, the difference between a class and an object. A class is like that blueprint. It's a set of instructions. An object, on the other hand, is the actual instance created from those instructions. Just like you can build many different cars from one single blueprint, you can create many objects from one class. Inside these classes, we define two things: attributes and methods. Attributes are the data, things like the car's color or speed. Methods are the behaviors, the things the car can do, like drive or honk. Finally, we have the __init___ method. Think of this as the factory line. It's a special constructor that runs automatically to set up the object's initial state using the self keyword to keep track of its own data. It's the starting point for every object we create. Now that we've mastered how to initialize individual objects with the self keyword, let's look at how we can organize them into hierarchies. On your screen is the OOP Builder, a visual way to see how classes share and adapt behavior. Try dragging the speed attribute and the make_sound method into the animal parent box. Notice how the dog and cat boxes below instantly update. This is inheritance. The subclasses inherit everything the parent has without us writing a single extra line of code. I'm adding this to our summary. Asterisk, asterisk, inheritance, asterisk, asterisk creates a is-a relationship. Since a dog asterisk is dash an asterisk animal, it automatically gets everything an animal has. This is the key to keeping our code clean and organized. But here's the clever part. Even if they both inherit make_sound, a dog barks and a cat meows. Go ahead and click make_sound inside the cat box to change its behavior. By overriding the parent's version, you're demonstrating asterisk asterisk polymorphism asterisk asterisk, the ability for different classes to respond to the same command in their own unique way. So, the interface stays the same, but the internal logic changes. It's like how a play button works on a music player versus a video player. The action is the same, but the result depends on what is being played. It makes the entire system much more flexible, doesn't it? Exactly. Feel free to add more attributes or create another subclass to see how the tree reacts. Take a moment to experiment with these overrides. Understanding this flow is what separates a Python coder from a Python architect. Now that we've mastered the architecture of classes and object orientation, it's time to unlock some of the most powerful meta-programming features in Python. Today, we're diving into decorators and generators, tools that will truly separate your code from the beginners. First, let's look at generators. Instead of creating a list and filling it with data, we use the yield keyword. This allows Python to produce items one by one, only when they are requested. As you can see here, this is the secret to processing million-item datasets lazily. Because we aren't loading everything into RAM at once, we don't exhaust our system resources. Take a look at this comparison chart. The memory footprint of a list grows linearly with the number of items, but a generator's memory usage stays flat. It's like the difference between buying an entire library and just checking out one book at a time. Next up are decorators. These are essentially wrappers that let you add logic like logging, timing, or access control to any function dynamically without actually changing that function's source code. It keeps your code clean and DRY. Don't repeat yourself. Finally, we have context managers, which you'll recognize by the with statement. These are critical for resource management, ensuring that files or database connections are always properly closed, even if your code encounters an error in the middle of a process. Building on our discussion about managing resources like files and connections, let's dive into how we handle the unexpected situations that inevitably arise when those processes fail. This brings us to error handling and debugging. Our ultimate goal is to write robust code that doesn't crash unexpectedly. It's about making our programs resilient and professional, ensuring they can recover gracefully from errors. The fundamental tool for this is the try, except, finally block. We wrap our risky code in a try block, essentially telling Python, give this a shot and see if it works. If a problem occurs, the except block catches the error, acting as a safety net so the whole program doesn't come to a grinding halt. Then we have finally. As we mentioned on the previous page regarding resource management, this block runs no matter what, making it the perfect place for closing files or database connections. It's important not to just catch any error. We should target specific ones like value or tighter pair. This precision helps us provide better feedback and prevents us from accidentally hiding other bugs. Finally, we can raise our own custom exceptions for unique scenarios in our apps and use a debugger to step through code line by line when we need to see exactly where the logic diverges from our expectations. Before we move on to the next checkpoint, I want us to think about a philosophical trade-off in software design. Now that we've mastered handling those tricky errors, we can start thinking bigger. Python's true power isn't just in the core language, but in its massive ecosystem. Experts don't reinvent the wheel. They leverage specialized libraries to build complex applications with incredible efficiency. In the world of data analysis, Python is the industry standard. Libraries like Pandas and NumPy, which we've mentioned briefly before, allow you to process millions of rows of data and perform complex mathematical operations in just a few lines of code. If you're building for the web, frameworks like FastAPI and Django have you covered. FastAPI is modern and incredibly fast for building APIs, while Django provides a comprehensive batteries-included approach for full-scale applications. For automation and scripting, tools like Selenium and the built-in OS module turn Python into a powerful tool for controlling your computer and automating repetitive browser tasks, saving you hours of manual work. Finally, to manage all these libraries, experts use virtual environments with pip and venv. This keeps your project dependencies isolated and organized, ensuring that your code works the same way on every machine. It's an essential habit for professional development. The sheer scale of this ecosystem is what makes Python so versatile. Looking at these different paths, I'm curious about your perspective on which area has the biggest impact on the software we use every day. Now that we've discussed how Python differentiates between types like integers and floats, let's see how that looks under the hood in our interactive variable lab. On the left side of your screen, you'll find a simplified code editor, and on the right, a visualization of your computer's memory stack. Let's start simple. Go ahead and type x equals 10 into the editor. Notice how a box labeled x immediately appears in the memory stack on the right. It shows the value 10 and correctly identifies it as an int or integer. Python is handling that identification for you instantly. Now let's test that dynamic typing we just covered on the previous page. On a new line, type x equals 20.5. Watch the memory box for x. See how it changes color and updates its type to float? In Python, a variable can change its type at any time just by assigning it a new value. I see our note taker is already marking down that dynamic means changeable. While you're at it, let's try some arithmetic. Create a second variable by typing y equals 5, and then try total equals x plus y. Look at the total box in memory. Since x is a float, notice how Python automatically makes the result a float too. Spend a moment experimenting. Try assigning a name in quotes, like name equals Python, and see how the memory stack reacts. This visual connection between your code and the memory stack is key to understanding how data is stored as we move into more complex logic. Great work exploring the lab. Seeing these variables update in real time reinforces that in Python, names are just labels pointing to data objects. Once you're finished experimenting with these assignments, we'll take this foundation and learn how to make decisions with it in our next section on control flow. From our very first lines of code to the complex task manager we just finished, you have made incredible progress. This is the final step of our session today, mapping out your continued journey toward Python expertise. Reflecting on what we've covered, we moved from the absolute basics through logical flow into the architecture of object-oriented programming, and finally to those expert patterns. This roadmap is your foundation for everything you'll build next. To keep growing, I've listed some top-tier resources here. Real Python offers fantastic deep dives. CS50 is perfect for computer science fundamentals, and the 100 Days of Code Challenge is the gold standard for building consistent coding habits. Always remember, the best way to learn is to build. Theoretical knowledge is important, but your true growth happens when you're debugging a real project and solving actual problems. Look at this mountain peak. You've climbed quite a distance today, but in the world of programming, there is always a higher summit. The view from the top is worth every bit of the effort. Thank you for your energy and focus throughout this course. It's been a pleasure guiding you through the Python ecosystem. Keep climbing, and I look forward to seeing the amazing software you'll create. Class dismissed.